In the previous video, we discussed nitrogen chemistry. We will now discuss the chemistry of phosphorus. Unlike nitrogen, phosphorus does not have a significant gas phase. Also, pure elemental phosphorus is unstable and is therefore very rare. In the environment, phosphorus occurs almost exclusively in the form of orthophosphate, or in short, phosphate. A phosphate chemical group, or moiety, includes 4 oxygen atoms bounded to 1 phosphorus atom, creating a stable orthogonal structure. In wastewater and natural water, phosphate occurs in both organic and inorganic forms. Organic phosphate is part of some carbon-based organic molecules, like the cell's membrane. Inorganic phosphate is not a part of any organic molecule. Rather, it appears as phosphate species dissolved in water or in phosphate-containing solid minerals. Raw sewage contains both organic and dissolved inorganic phosphate. These are interchangeable in the wastewater treatment plant. When bacteria degrade organic matter, organic phosphate is released and becomes inorganic phosphate. When bacteria produce proteins or multiply, they take up inorganic phosphate and convert it to organic phosphate. A major challenge in biological phosphorus removal is to increase phosphate uptake by bacteria. Dissolved inorganic phosphate mainly occurs as weak acid species that participate in proton association-dissociation reactions. 4 inorganic phosphate species make up the phosphate weak acid system. Phosphoric acid, H3PO4, is the most acidic solute. It can dissociate 3 protons. Thus, this system is considered triprotic. In the first proton dissociation reaction, phosphoric acid transforms to dihydrogen phosphate, H2PO4-, a monovalent anion. This is an acid-base equilibrium reaction with a dissociation constant Ka of 10 to the minus 2.14. Accordingly, the pKa, or minus log Ka, is 2.14. In the second proton dissociation reaction, dihydrogen phosphate becomes hydrogen phosphate, or HPO42-, which is a bivalent ion. The pKa for this reaction is 7.2. The third proton dissociation reaction converts hydrogen phosphate into phosphate, PO43-, a trivalent ion. The pKa for this reaction is 12.37. With all these equilibrium constants, we can determine the concentration of different phosphate species as a function of pH. This graph shows the percentage of the phosphate species out of the total inorganic phosphate. As you can see on the left side, phosphoric acid is dominant at a very low pH range, lower than 2. On the right side of the graph, you can see that phosphate ions are dominant at very high pH values, higher than 13. These extreme pH values are not typical in wastewater that usually have pH values between 6.5 to 8.5. Therefore, the dominant species of inorganic phosphate in wastewater are hydrogen and dihydrogen phosphate. Looking at this graph, it may seem that the concentration of phosphate ions is 0 at the relevant pH range. However, this is not the case. As seen in this graph, showing the log concentration of phosphate species, the phosphate concentration is low but not 0. Even at this low concentration, the presence of phosphate ion is significant. When phosphate reacts with certain metal ions, solid mineral phases can precipitate out of the solution. Iron phosphate and calcium phosphate minerals are particularly important because of their low solubility. Hydroxyapatite and vivianite are examples of such minerals. Once phosphate ions are removed from the solution, the system will maintain acid-base equilibrium. This means that more phosphate ions will be generated through proton dissociation, and the precipitation will continue. As a result, most of the inorganic phosphate can be immobilized in these minerals, given that enough metal ions are present. In calcium-rich soils, for example, phosphate is immobilized in minerals that are not readily available for plants or bacteria. This complicates plant nutrition, but also prevents phosphorus pollution to some extent. Iron phosphate chemistry can be utilized for the removal of phosphate, as further explained later in this class.